Hello, I'm Hailsong, a PhD student at KAIST UVR Lab, supervised by Professor Wontak Wu. Today, I will present our work, VR Gaussian Avatar, integrating 3D Gaussian avatars into VR. In this work, we design a real-time, HMD-only controllable 3D Gaussian avatar system, and validate it through both quantitative evaluation and user studies. Let me start with a simple question. In social VR, what makes an avatar feel like you? Is it motion fidelity? Is it visual appearance? Or is it responsiveness and latency? If you have ever used social VR, you already know the answer: it's all of them. Traditional mesh-based avatars are fast and compatible with existing VR pipelines. However, they often fail to preserve subtle appearance details, especially in clothing, hair, and fine facial features. On the other hand, recent neural rendering methods, such as NeRF and 3D Gaussian splatting, achieve remarkable photorealism. But in practice, these methods are rarely used for interactive, full-body VR avatars. For the neural rendering, stereo rendering doubles the computation. Animating neural primitives is expensive, and existing VR pipelines are not built for neural rendering, especially under HMD-only control. In other words, photorealism alone is not enough for VR. To bridge this gap between realism and interactivity, we designed VR Gaussian Avatar, which delivers high-fidelity 3D Gaussian avatars with real-time, HMD-only control and efficient stereo rendering for practical VR use. Here is the overall architecture of VR Gaussian Avatar. On the left is the offline reconstruction stage. From a single image, we reconstruct a canonical 3D Gaussian avatar using the large animatable human model. During this process, Gaussian parameters and animation-ready rig bindings are generated. Once reconstructed, this canonical avatar remains fixed. On the right is the runtime pipeline, where two components operate in parallel. The VR frontend receives head and hand tracking signals from a commercial HMD. Using inverse kinematics, it reconstructs a full-body pose and derives stereo camera parameters. Each frame, it streams the pose and stereo view parameters to the GA backend. The GA backend then deforms the canonical Gaussian avatar and performs real-time stereoscopic rendering. The key idea behind this architecture is to decouple motion estimation from Gaussian rendering, while keeping them tightly synchronized through a lightweight streaming interface. This separation is critical, because VR demands both high visual fidelity and strict real-time responsiveness. By decoupling motion estimation and rendering, we satisfy both requirements simultaneously. The key to making this system real-time is what we call binocular batching. In VR, stereo rendering usually works by rendering the left eye and then the right eye. Which means you essentially do everything twice, staging Gaussians, launching kernels, and transferring memory. That's expensive. Instead, we render both eyes together in a single batched pass. Gaussian attributes are staged once, and projection is evaluated for both eyes within the same step. This removes redundant computation and improves efficiency. At 1024 by 1024 per eye, we achieve about 39 FPS with batching, compared to 25 FPS without it. In VR, maintaining high frame rates is essential for user comfort and immersion. Binocular batching directly addresses this requirement. Based on this design, our contributions are threefold. First, we introduce a decoupled architecture that enables real-time control of 3D Gaussian avatars in VR. Second, we propose binocular batching for efficient stereo rendering, making real-time performance feasible. Third, we provide perceptual validation through controlled VR user studies, demonstrating improved embodiment and plausibility. Here is VR Gaussian Avatar in action. You can see the fine appearance details and smooth full-body motion in real time. This illustrates how we achieve both realism and responsiveness in VR. To evaluate our system, we compare it against two mesh-based baselines. The first is a video-based reconstruction pipeline. For the head, we use Fate to reconstruct a detailed facial model, and for the body, we use RCSMPL to recover a textured SMPLX avatar from RGBD video. The second baseline is an image-based reconstruction pipeline. Here, we recover the body shape using SMPLX and generate textures with TextDreamer from a single image. Importantly, all methods including ours are driven using the same HMD-only tracking setup. This ensures that any difference we observe comes from the avatar representation itself, not from differences in motion control. To evaluate the perceptual impact of our system, we conducted a 2x3 within-subject study with 24 participants. The factors were avatar type, self versus other, and reconstruction method, ours, video-based, and image-based. Participants performed a mirror-based avatar control task in VR, following audio instructions such as raise your left hand or look at your mirrored face. After each condition, they completed standardized questionnaires assessing embodiment using VEQ, plausibility using VHPQ, and motion quality. This allowed us to quantitatively compare perceptual differences across avatar types and reconstruction methods. Here are the main findings. First, our method significantly improved body ownership and agency compared to both baselines. Second, it achieved higher plausibility and motion synchrony, with consistent gains across both self and other avatar conditions. Overall, these results show that the improvement is not merely visual, it meaningfully enhances embodiment. In terms of reconstruction quality, our method achieves superior image similarity across all metrics, including L1, LPIPS, PSNR, and SSIM. We also observe consistently better visual fidelity in qualitative comparisons, with sharper details and more faithful appearance reconstruction. To conclude, we presented VR Gaussian Avatar, a real-time, HMD-only controllable 3D Gaussian avatar system for VR. Our work demonstrates that 3D Gaussian splatting can move beyond offline rendering and become practical for interactive VR. If you're interested, feel free to reach out and discuss further. We will also be showcasing a live demo of our system at the demo booth during the conference. Thank you for listening.